In any case, so I'll be talking about, so this is work that I've done with my supervisor, Elizabeth, and Dr. Bernard and Professor Crispino from the Federal University of Pará in Brazil. And we'll be talking about quantum superradiance on static black hole spacetimes today, really, Rising-Nordstrom spacetime. So what is superradiance? Well, it's a radiation enhancement effect in an otherwise dissipative system. And it occurs in a variety of physical phenomena: superfluids, superconductors, even sonic booms within shock waves are associated with it. What I'm particularly interested in is black hole superradiance and in a field black hole system. And you may be wondering, well, where's the dissipation coming from? So if you remember back to, perhaps you might have studied the Schwarzschild solution at the end of your GR course, where the dissipation is provided by the potential barrier of the black hole. Now, we're going to study Rising-Nordstrom black holes, which are otherwise known as charged black holes. And one of the important things here is superradiance occurs because of the interaction of the black hole charge and the scalar field charge. So we therefore require a charge field. If we didn't have a charge field, there would be no superradiance. And there'll be a lot of information in this talk. What I would really like people to sort of focus on, or the take-home point essentially, is that we'll see that in classical superradiance sort of corresponds to stimulated emissions. You can imagine a sort of a field mode coming in from far away from the black hole, i.e. infinity, reaching this potential barrier and then being either transmitted or scattered back. And when it's scattered back, it's with greater amplitude. That's essentially classical superradiance. So it's a sort of stimulated effect. And when we quantize this system in line with quantum field theory and curved spacetime, we'll see that it corresponds to spontaneous emission. So unfortunately, there is a bit of mathematics that we have to do. Equation 1 is the it's the metric of Rising-Nordstrom spacetime. This is quite similar to Schwarzschild spacetime, with the exception of this extra term in the metric function, which is proportional to the square of the charge of the black hole. Now, we'll only be considering the sub-extremal case. George spoke very nicely about the extremal case. The super-extremal case, where the charge of the black hole is greater than the mass, actually gives rise to a naked singularity. So we don't think it's physical. So we'll restrict our attention to the sub-extremal case. And in this case, the metric function has two zeros at R plus and R minus. So R plus is the location of the familiar black hole event horizon, and similar to Schwarzschild spacetime, the metric function vanishes on the event horizon. The details of R minus are not important for this talk, but this is the Cauchy horizon, and what it essentially is where determinism ends. So your past no longer determines your future. Now, moving on, this is a Penrose diagram of Rising-Nordstrom spacetime, and I've been slightly mischievous here because this is the maximally extended Rising-Nordstrom solution, which one really requires critical coordinates for. But if we restrict our attention to region 1, which will be the focus of this talk, then I'd like to draw your attention to this surface in particular, which is past null infinity, so far away from the black hole in the past. This is the past horizon, so near the black hole, again in the past, and future null infinity. So this is far away from the black hole in the future. And we're going to think about waves incoming from past null infinity, how they respond to the potential barrier, and whether they scatter back to future null infinity with a greater amplitude. So the dynamics of the scalar field are governed by this Kleingordon equation here, where we have the gauge covariant derivative and I should say a background gauge potential, which is left classical throughout. And this equation admits a separable solution in terms of scalar field modes. Now, Rising-Nordstrom spacetime is static, so we have a harmonic time dependence. It's also spherically symmetric, and that means that the angular function is given by the spherical harmonic. So really, NW is a normalization constant. So really the physics is contained within the radial function here. So when we substitute that ansatz into the scalar field equation and solve by separation of variables, what we eventually obtain is a radial equation here. And this may be familiar from Schwarzschild space-time. It's in the form of the famous Reggie Wheeler equation. And this effective potential is this sort of the potential barrier felt by a scalar field mode. So it has the form given in equation 7, and it takes, most importantly, we want to see how a scalar field mode incoming from far away from the black hole near infinity, how that sort of transmits through or is reflected from the potential barrier. So it's interesting to look at its asymptotic values. So near infinity, the first term vanishes because R is very large. We can also ignore the 1 over R term in the second term. And so we're left with the effective potential tends to minus omega squared. Near infinity, f of R plus is equal to 0. So we could ignore this, but we can no longer ignore this term. And so we have this minus omega tilde squared term. Now, this is different from Schwarzschild space-time. And this difference in effective potential near to and far from the black hole is what's going to give rise to superradiance. So at the risk of making more formal mathematicians very unhappy, we can derive a set of field modes which you can sort of imagine as basis vectors on a sort of 2D vector space. That's obviously very heuristic, but what's important is that with these two field modes, we can expand the field in an orthonormal basis, which we require for quantization. And in particular, if I can draw your attention to the A and B coefficients, these are reflection and transmission coefficients, respectively. So if we look at the in modes, which corresponds to a scalar field mode coming up from past null infinity with unit flux, we can see that some part contained in the A is reflected back to future null infinity, and some part governed by the B coefficient is transmitted through the potential barrier down the horizon of the black hole. So moving on. Now, if you know what a Wronskian is, great. If you don't, it doesn't matter. But what we can do by evaluating the Wronskian of the radial equation near to and far from the black hole is derive this relation here. And what you can see is, if we remember that omega tilde is equal to omega minus QQ over R plus, where we have the product of the scalar field charge and the black hole charge. So they're not necessarily have the same sign. When they do have opposite signs, so when this product is less than 0, the transmission coefficient will be greater than 1. And so an incoming scalar field mode from past null infinity will be reflected back to future null infinity with a larger amplitude than it had originally. And so we've got a plot of this. I should remind you that when Q is equal to 0, so this Schwarzschild space, we reduce to the Schwarzschild case. Sorry, that's not strictly true. That's just a scalar field charge, but there's no superradiance when Q is equal to 0. But when we increase the magnitude of the scalar field charge, then we see a greater superradiance scattering. So our discussion, is that 2 minutes?
Yep.
Oh, wow. Okay. So our discussion thus far has been classical. And thanks, George, for explaining that there's no unique vacuum state in curved spacetime. So there's 3 major states in Schwarzschild. We're going to talk about the Bowler state, which sort of corresponds to our familiar notion of an empty state far away from the black hole. But given classical superradiance, even if it's empty at far away in the past of the black hole, it may not necessarily be empty at future null infinity. And the way we're going to examine this is to define a state that's definitely empty at scry minus and examine the fluxes at future null infinity. So this is a horrendous slide, don't worry. This is essentially like the terms and conditions of the talk. You're never going to read the whole thing, but I'm sort of legally obliged to give it to you anyway. What I would like to draw your attention towards is the limits of this integrals in the expansion of the field operator. So a priori, one might think that there's a contribution to quantum observables from all field modes, and we'll see whether that's true in a couple of slides. So I'm going to whiz through this slide because I haven't got much time left, but we can essentially, there's two interesting quantum observables. One is the current operator, the other is the stress energy tensor, and these govern the back reaction on the electromagnetic field and the space-time geometry respectively. Using the expectation value of the flux components of these observables, we can derive expressions for the fluxes of charge or energy observed by the black hole by an observer far away. And if time. Oh dear, right. I'll just finish off quickly. That's all right. Well, so we can derive expressions using the sort of asymptotic expressions of the scalar field modes. And the first thing to note is that these are not zero. So the past polar state's clearly not empty at future null infinity. And this is essentially the phenomenon of quantum superradiance. So there's no sort of stimulated emission. In fact, what we've defined is a state that's definitely empty in the past of the black hole, and yet we have a non-zero flux of charge and energy in the future of the black hole. And this is a non-thermal distribution, so it's not Hawking radiation. And finally, here are a couple of plots. You can see that the superradiant emission acts to discharge and lessen the energy of the black hole. Thank you for listening, and apologies for overrunning.
That's okay. There's a quick question in the Q&A. Is there a typo in the Wronskian subscripts? I think this was when you introduced the Wronskian.
There may well be. Yes, I can see one immediately here. That should be DX1.